Okay, we're ready to start. Yesterday we saw a number of tests that are frequently used. Many of them are built as maximum likelihood ratio tests. But there are other ones. One is, for example, the Kolmogorov-Smirnov, and we saw a variant of it, the Lilly force, for testing whether a distribution is normal. There are 2 or 3 other tests that are very frequently used and are very convenient. One of them is called the median test. It's not new for us. In fact, we have already discussed the case where we want to test whether a certain distribution xi is, roughly speaking, 0. Is there an improvement in something? Paired data, for example. One way to look at it is to find a confidence interval for the median, and we have discussed already yesterday that deciding whether 0 is in the confidence interval is the same as designing a test that has H0, the common distribution as median 0, versus H1, the common distribution has non-zero median. So nothing new. It's called a robust test because it makes no distributional assumption. Here, the only thing we discuss is whether the median is 0 or not. So that's the most robust test we can think about. I applied it again for this data, and I found that I reject H0, so there is an improvement, which is the same result as we had found with other tests. There are variants of this that all try to exploit statistics that are robust, that don't make the assumption of normality, Gaussian distribution, that we saw in some of them. We'll see 2 of them. Here's one of them. It's called the Wilcoxon rank sum statistic. So if you look at the small letters, here is the description. But perhaps the more interesting thing is to know what are the hypotheses of the test. The hypotheses of the test are under H0, so I have 2 series of data that are not necessarily of the same length, so they are unpaired experiments. And I want to say, for example, if y is obtained after doing something different than x, is there an improvement by doing this thing different? Does the treatment, in medical terms, improve, or does the compiler option improve our performance here? The null hypothesis is no, both have the same distribution, and the H1 distribution is they differ by a location shift. Location shift means they have the same distribution but shifted over the x-axis. Then the idea of this test is to use the order statistics of the joint thing. So here there's a typo. I should have called it x1 and x2. So what we do is we take all the numbers we have obtained of those 2 bags of numbers, and we sort them globally from the first to the last. So if I have n1 numbers here, n2 here, I have n1 plus n2 numbers. I sort them globally, and I call R the sum of the ranks of the first sample. Right. If the 2 samples come from the same distribution, then there is no reason that the data in the first sample are smaller or larger than the others, so they are equally spaced. They should be ordered uniformly. So the ranks of the first sample should be uniform in n1, between 1 and n1 plus n2. So given that, if it's uniform, we can compute, under the H0 assumption, we can compute the distribution. It's a somehow complicated exercise, but that was done once by someone and verified by reviewers. We find that this distribution here is independent of the distribution of x and y, because it's only about ordering things. So if you take n1 and n2 numbers, you sort them. If they come from the same distribution, then the ordering will be the most random one. So the sum of the ranks of the first n1 will have a well-known distribution that depends only on n1 and n2. It's well-known, it's tabulated, you can obtain it in software packages, but it's a bit awkward to compute. But for large sample size, when n1 and n2 are both large, this is approximately Gaussian, with a mean given by this formula and a variance given by this formula. Therefore, the number r should be around this mean. If it deviates significantly compared to the square root of v here, if it deviates significantly from that, then we can declare that h1 is not true, which is captured by the value for the p value. The p value is obtained by this. You recognize a form that we saw in a quiz yesterday. This is the p value that we obtain when the rejection region is the absolute value of r is larger than something, which means that whether r is very small or very large. So if r is far from m in either direction, we reject, which gives this p-value, as we have discussed yesterday. I tried it for this here, where I had before done an ANOVA test. The ANOVA test was assuming Gaussian. Here it's not assuming Gaussian. We found p-values that are very, very close to the ones we had with the ANOVA test here. So there is not much difference. There's a benefit here. We're not making the Gaussian assumption, so it's more robust. If we generalize this to more than 2 samples, red and blue, but perhaps k groups here, the test changes name. Instead of Wilcoxon rank sum, it's called the Kruskal-Wallis. So it's similar, and it tests whether all the bags of data we have come from the same distribution or they differ by a location sheet. We will conclude with this last test that sometimes we might find useful. That's a test of independence, or more precisely of independence and identity. So whether a given sequence of numbers that we have is IID. Right. So we assume those are numbers, and what we want to test is whether it's IID. We saw methods for doing that are based on autocorrelation functions. We can compute, we first convince ourselves that it looks stationary, then we estimate the autocorrelation coefficients, and if it's IID, they should be all within less than error bounds that are found, and this can give also a test. Here, this test is more robust and doesn't rely on computing autocorrelation coefficients. Autocorrelation coefficients have the problem that they can be polluted by large outliers. If some values are very large, because they are based on square, this can have a large impact. This one is based on something similar to ordering. It's based on what is called turning point. What is a turning point? A turning point is something you can observe when you look at 3 consecutive values in your time series. So if you have 3 consecutive values, and here I'm ordering them by magnitude. Here it means the first one is larger, the second one is the middle, and the third one is the smaller. So if I take 3 consecutive values, I can order the 3. And there are only factorial 3 possible ways they are ordered. They're all given here. Right? It can be that they are in this order, in decreasing order, or in increase order, or any permutation of the order here. So it may be that the max is the first, or here the max is the second, or here the max is the last, etc. So you have 6 possible cases. We say that there is a turning point. This test says there is a turning point if we are in any of the 4 cases in the middle, because we decrease, then we increase, or here we increase, then we decrease. So we say we have a turning point. If the data is IID, then there is no reason that xi is larger than xi minus 1, or vice versa, because they are drawn independently from the same distribution. So there is some variability. Whether the variability makes the first larger or the first smaller, that should be equally likely. So if the points are truly IID, then all 6 cases should be equally likely to occur. They should have the same probability. Given that, with a bit of work, we can prove that it means that the number of turning points under H0, same as for the Wilcoxon rank sum test, can have a distribution that is well-defined and independent of anything else. And for n large, it's also approximately Gaussian. with this mean that is given by those numbers. So as you can imagine, those are interesting combinatorial problems to compute those things that we will not cover. But once this is known, as for the previous case, we can compute a p-value and therefore test whether our data is IID. In fact, it's not exactly IIDness that we test here, but a slightly weaker property, which is called exchangeability, which means that if I change the order of the data with any arbitrary permutation of the data, it doesn't change the distribution. Right? So if I give you x1, xn, or if I would shuffle the numbers in any order, then you cannot see a difference here. That is what is really tested. Of course, if it's IID, it gives this. Voila, that's all we will see about tests, almost. So tests are useful to quantify whether a difference is significant or not. Typically, we do it when the difference is small, because if the difference is large, by providing confidence intervals of something, perhaps simply the mean or the median, or if we have a more elaborated model that we can fit to the data, that will give us more information. It will not only tell us whether the difference is significant statistically, so remember statistical significance simply means whether this significance can be explained by noise, by the natural randomness of things, or whether because the two things are really different. This is what a test will tell us. The test will tell us whether it's physically significant, right? A difference might, if we have a large number of data, perhaps B is better than A by a minuscule improvement, but since we have so much data, we can see the difference is statistically significant, but perhaps practically not so significant. Or very often we have the reverse. The difference is physically insignificant, and the test is unable to make the difference. Like everything we do with statistics, there are assumptions in the tests, very often Gaussian, for example, so they need to be discussed, whether they make sense for the data we have. We should not be too dogmatic about those. If the thing is approximately normal, then we should accept it. But if the thing is heavy-tailed, for example, very far from normal, perhaps the test does not give us the right answer. And I would invite you to, after the course, go to this website here, where you have two statisticians who are here, so two professors of statistics, who answer one question on tests. So the question is, do we still need a statistical threshold value? This is what they call, what we call the 0.05. Yeah, right. So when we do a test, we compute the p-value. If the p-value is less than 0.05, we reject the null hypothesis. Right? Does that make sense or not? No. Read what those two statisticians say about it, and we can talk again next week. As you will see, there are some controversies about tests. Voilà, that's all for the module on tests. Are there any questions? No? Then without further ado, we move to the next topic, which is model fitting again. There is one or two important things, one and two particular here, that we will discuss. When we do model fitting, one of the things we often have to do is to choose a distribution. Very often we don't need to. If we do bootstrap or Monte Carlo simulation, we can use the data we have. But sometimes if we want, it's very convenient to reason about things, to model things, saying, if I have my data that is random and coming from this distribution, then I can easily do simulations or even analysis sometimes. So what we will discuss is what are the important things to know about distributions before choosing one. And those important things are the shape, classical indices called Curtosis, Skewness, power laws, and the hazard rate. So those are different distributions, are different with respect to those statistical properties. What are those statistical properties? Well, a shape is what remains when you rescale and shift. If I give you two distributions given by the PDFs here, I can interpret one of the distribution of a random variable capital X, and the other one by a random variable that differs by a shift. So I offset the values and I rescale and multiply by some number. So S is typically positive here, and M is positive or negative. When we do histograms or CDFs, MATLAB normally automatically chooses the boxes here. So if I rescale and reshape, I ask MATLAB or NumPy to do a plot, the plots will look exactly the same. So the shape is what remains invariant when we ignore the scale and the values on the axis here. For example, here are three distributions. The standard normal distribution, zero mean unit variance, and then arbitrary Gaussian distribution, and then the very special case when the variance is zero. Which distributions have the same shape? Well, the answer is that's true. A and B have the same shape. In fact, it's just a shift and a change of scale here. Here it's a more radical change. This is a constant, right? This is given whether mu is non-zero or not. This was just to fool you. Here are the distributions. If I plot the PDF of the standard Gaussian, the PDF of another Gaussian, of course they don't look the same because some is thin, some is fat, but it's just an artifact of changing the y or x axis. Except this one, which is also called sometimes a Dirac distribution, which is a complicated name to say something very simple. It means with probability 1, it is given to the value, whatever the value here, -6 here, for example. So first take-home message, all the Gaussian distributions, when sigma is positive, are the same. They have the same shape, they are just differing by a shifting and a change of scale. So when you go through a catalog of distributions like Wikipedia is very good most of the time, but sometimes it's unnecessarily complex. This is one of the cases where it's unnecessarily complex. Wikipedia will give you all the possible values of all parameters of all distributions, but once you have a distribution that has a given shape, there's no need arguing and discussing the properties of the other instances of the distribution that have the same shape. If you want to compute the variance, for example, of something that has been rescaled by S, like here, right? If I multiply X, what is the variance of Y with respect to the variance of X? What's your answer? It is?
S squared.
Yes, S squared times the variance. So when we change the scale, it's like changing the unit. If we measure in millimeters or in meter, we change the values, so it's like changing the scale. The variance is in the unit square. We change the scale, we change also the variance by the same scale. And if we shift by M, the variance is not modified. So all properties of the distribution are completely derived in a straightforward way from the distributions of the standard distribution. So the only distributions we need to really study the properties of are the standard versions of the distribution. For example, for the exponential distribution, what can we say? If you look at a catalog of distribution, if you go to Wikipedia, you search for the exponential distribution, you will find it has one parameter, lambda. Is it a scale, a location, none, or both? What do you think? Look at the graphs, all the exponential distributions are on the same interval, 0 plus infinity. So there's no location shift when we change lambda. Right. But that's truly a scale parameter. For example, we can see that if we take the standard exponential distribution of parameter 1, then 1 over lambda x gives the generic distribution of parameter lambda. We can do that by looking at the PDF, or if we remember how we sample an exponential distribution, we say we do 1 over lambda log minus log of u, where u is a uniform random number. So 1 over lambda is truly a scale parameter. So there is in fact only one interesting exponential distribution, it's exponential of 1. But we discover also that there might be other interesting distributions that are not given here. If we shift the exponential distribution, if we shift it to the left, then we will obtain something that is between minus a number and plus infinity, which doesn't have a name other than a shifted exponential distribution. If we shift it to the right, we similarly have something that has a minimum value here. And I think in the homeworks we have looked at what are the relationship to conditional distributions, for example. I mentioned that if I have a change of shift and scale, I can easily derive everything. Well, can we derive the PDF, for example? What is true? So the question is, if we do a change of variable inside the distribution, what is the result on the PDF? Right? It's one thing we often need to do, so it's important to be able to do it. So I do a change, so it's one easy way to reason about random variables. The new random variable is a linear transformation with an offset of the previous one here. What is the PDF of y given we know the PDF of x? So I call, for example, capital F CDF or little f the PDF of it. One way to think of a PDF, that I think we've already discussed, is this one. If I take any test function phi, for which the integral makes sense, for example, because it's bounded, the expectation of phi of x is given by this formula. It's one of the basic formulas we see in probability. When I have to compute the expectation of a function of a random variable, I compute the integral of the function of x multiplied by the PDF. But in fact, if you are able to do that, it is something that defines the PDF. If this formula is true for some function f, it must be the PDF. Now, I take as function of x, I take a function of y, which itself is a function of x. So if I take an arbitrary test function, and I say y is this transformation, I obtain this thing here, right? Which is the integral of phi of sx plus n f of x dx. Right? And now I need to express that as something that is a function of phi of something multiplied by something else, right? Which is not the form. The integration variable should be, this should be the integration variable, which means I need to do a change of variable. I call this little y, which is the same change as we do here. And then by integration 101, if I do this change of variable in the integral, dy is s dx. S is positive, I'm assuming here. So the order of the bounds doesn't change, and this integral is equal to that. Here. That's the change of variable in the integral. Now if I look at the beginning and the end, expectation of phi of y is this. So I wrote it as a function of my test function of y multiplied by something. So this something is the PDF of my random variable, capital Y. So the PDF is given by 1 over s fy minus n over s. So this is the formula that we have. So there is Of course, the argument is rescale, but the scale factor also comes, or 1 over the scale factor comes in the PDF, which is something we have seen, for example, here. Oops, where am I? Here you see that when we rescale, we also change the scale on the y-axis of the PDF. Right? We change on the x-axis because the mean now of the blue is more on the left, the mean of the red is more on the right, but we change also the values on the x-axis. And similarly for the Gaussian distribution that we had done before. There are other techniques to derive the change of variable. This is one of them, in case you don't remember it, but there are many different ways to derive this. A good catalog of distribution should therefore have only a standard distribution. Sometimes this is well defined, what is the standard. For example, for normal, exponential, and uniform, I think most people would agree that the standard uniform distribution is this one, the standard exponential is this one, and the standard uniform is that one here. Very often, we are using also the log normal distribution. The log normal distribution is something we have used implicitly when we looked at file transfer times, for example. We looked at the file transfer time, we said they had huge variability, but if we take the log of the file transfer time, they seem to be much less variable. In fact, they would be close to normal. So that's an example of a log normal distribution. So we say that the random variable x has a log normal distribution if x is the exponential of z, where z has a normal, which means Gaussian, distribution here. Or in other words, if log of x is normal. So log normal means log of x is normal. Could be confusing, but this. So typically x may take very large values, but when we take the log, we kill the very large values and the thing becomes normal. So a log normal distribution is able to take very large value. Is a positive x is a non-negative number, right? A positive number, so it's only gives only positive values, and it is more likely to find large values than something like a Gaussian distribution, for example. We can simply also observe that any Gaussian distribution z can be expressed as mu plus sigma z0, where z0 is the standard normal distribution. Okay. Hence, we can say that any x is also equal to exponential mu, exponential z0 to the power sigma. Right. This is, for example, I'm showing here the PDF of the log normal distribution for various values of sigma here, and for mu equal to 0. So that are the different PDFs we find. Those are the different shapes of the PDF. Given that, what can you say about the log normal distribution? In fact, if we look at this formula, I mean, exponential z0 is one random variable, so it's a single distribution. Then what do I do to obtain the log normal distribution? Oh yeah, what did you vote for? We multiplied by exponential mu. So exponential mu is a scale parameter. So mu influences the scale of the distribution, right? So different values of mu simply means different scales. Right? But sigma is taking this to the power something. Typically, when we take something to the power, then it's a nonlinear transformation, except if sigma is equal to 1. So if sigma is equal to 2, then we take this to the square, right? If sigma is equal to 0.5, we take the square root. So we do very different transformation of this thing. So we should expect to change, in fact, the shape of the distribution by different sigma. So for the log normal distribution, right, exponential mu is a scale parameter. Mu does not affect the shape, but in fact every sigma gives a different shape. So we can do a bit of math and see that when we look at the PDF, for example, it's not possible to derive the PDF for different sigmas from one another. So take-home message, there are as many different log normal distributions as there are values of sigma. What are the standard log normal distributions? They are the one that we obtain when we fix the value of a shape. For example, if I fix the value mu to 0, I obtain a standard log normal distribution here. Well, that's a first important observation to do, that many catalogs will not tell you. When I say, for example, I looked at my data and I thought it had a shape that looks like Gaussian, okay, that's a valid argument, and then you need to fit mu and sigma too. But saying that the shape is a log normal distribution is, of course, much more stretched because there are many different log normal distributions. In fact, I have shown you the different PDFs. You see that when sigma is small, it looks almost like a Gaussian distribution, at least quantitatively. When sigma is large, it looks almost like an exponential distribution, because the exponential would not go back to 0, it would stay here. But apart from this little thing here, it looks very similar to an exponential distribution. So the log normal distribution is in fact a whole class of distribution. It's not one distribution. So that's the ambiguity that is often used, even in the literature, between a distribution or a class of distribution. Another thing that is often looked at on distribution, so we've discussed the shapes. Now, if we want to say something about the shapes, there are two useful indices that are called skewness and curtosis. If I look at a distribution, I can compute its expectation, first moment, its standard deviation, and those two things are independent of the shape. Right? At least the values scale with the shape, but they're just scaling things. So they don't give us any information about which distribution to choose. If we go to higher order, third and fourth moment, they play a role. So the way the moments are defined, it's defined here, for example, the third moment is the expectation of x minus its mean to the power 3. So first we center the distribution, and we take the expectation of the cube. We can do the same for the fourth moment. For some reason, that will become apparent in a second, we modify it by the variance, which is the second moment here. The reason we do that is that for the Gaussian distribution, for a normal distribution, the kappa 4 is equal to 0. So of course the fourth moment is always positive. For the Gaussian distribution, the fourth moment is exactly equal to 3 sigma squared. So since the Gaussian distribution plays a central role, we consider the fourth moments relative to the Gaussian distribution. That's one interpretation. Those two indices, those two third and fourth moments are not unit free. So if x is measured in seconds, then kappa 3 is in seconds to the power 3. So to make them unit free, we divide them by the square root of the variance, sigma, which is in the units of the thing that we measure. And that has a name. It's called, for the thing derived from the third moment, it's called the skewness index. Why skewness? Because in fact it measures the symmetry of a distribution. If a distribution is like this or like that, so this is perhaps the log normal distribution for large sigma, then so it is slanted to the left or to the right. If it looks to be visually slanted to the left, we say the skewness is positive, otherwise we say the skewness is negative. So it measures, and if the distribution is symmetric, like the Gaussian distribution, then the skewness is 0. So that's one thing that is easily visualized. The kurtosis is a bit more contorted. The kurtosis is this rescaled by sigma to the power 4, because we're taking power 4 here. And if it is 0, or if the distribution is Gaussian, normal, then it is 0. The reverse is not true, but in one direction. So it's taken as a departure from the normal distribution. If two distributions have the same shape, what can we say about those two indices? The correct answer is C. They have both. So the skewness and kurtosis are properties of the shape of the distribution only. Why is that? Well, because if I shift, since I've removed the expectation here, if I shift by mu, then kappa 2, kappa 3, kappa 4 are the same. So the mu shift doesn't play a role. If I rescale by sigma, then the variance, if I rescale by s, the variance will be rescaled by s squared. So the sigma will be rescaled by s. So since we divide by sigma cube or 4, this will also disappear in the skewness indices. So those are properties that are truly properties of the shape. So they are useful in that sense here. So you have good catalogs of distributions like this one, which is publicly available freely on the internet, that will tell you for every distribution the skewness and kurtosis, for example. Wikipedia also will give you the skewness and kurtosis. And a way to see whether different distributions are truly the same shape or not is to look at one of the parameters. Here, for example, the skewness, which says how symmetric it is. This one is not symmetric. It's slanted to the left, but very little. It would be symmetric if it would go to minus infinity. It looks very much like a Gaussian distribution, but it is not. We have a positive skewness. Here we see very large skewness for this distribution here. The skewness, remember, is free of units. So it has sigma is not free of units, but the skewness is free of units. Since the index, the kurtosis index, is also an index of not being Gaussian, also this, I mean, if I have a Gaussian distribution, kappa 3 should be equal to how much? 0, because it's symmetric. So one way to test whether a distribution is Gaussian or not is to check whether kappa 3 and kappa 4 are equal to 0 here. So there is one test that does that. It takes the sample estimate of the skewness and kurtosis index, squares them, combines them in this formula, and there is a theory that says for n large this is approximately chi-square 2 if the data comes from a normal distribution. So it is 0 in theory. So what are those sample indices? Well, kappa 3, for example, is a theoretical index that you compute if you know exactly the distribution. Now, if I give you a sample of n data points, you can estimate this. What would be your formula for the estimate? How would you estimate this if I give you n data points instead of giving you the theoretical formula for the distributions? The sample mean. So it's an expectation of something. So one way to estimate an expectation is to do 1 over n, the sum of the values. Right? For one way to estimate expectation of phi of x is to say 1 over n sum of the phi of xn. So we do simply 1 over n x minus exponential expectation of x will be replaced by the sample mean. Like we take the sum of the cubes of all those divided by n, and similarly for order 4. So those are. Now if we do this, we will have values that are very close to 0 if the distribution is Gaussian, but is not exactly 0. So So the deviation from 0 is captured by this formula here. So as we did already a few minutes ago, that is used to do another test here. I did it again for the 2 samples we had, which we tested with various tests. We saw Lisa's test based on binning. We saw the Kolmogorov Smirnov or the improved Lilly-Force test. Here we can do also the Jarque Bera test, and we find very similar results. We accept that it's normal for the second, and we reject for the first here. Voilà, I think that's all we will see for today. How to screen distributions. What we will see next week is how in practice we can use distributions that can model very weird data samples that are not so weird. In fact, when we have large data samples collected over the internet, very often we find things that have properties like heavy tail that differ from Gaussian distributions. Well, we'll see how to manipulate those and what this tells us also. Voilà.